Today we're going to be looking at tutorial 3a. Question 9 is about matrix gymnastics. Consider the set of matrices. Tau1 is equal to 1 over root 2, 1, 0, 0, minus 1. Tau2 is 1 over root 2, 0, 1, 1, 0. And Tau3 is 1 over root 2, 0, minus 1, 1, 0. One of them does not have real valued eigenvalues. Use the characteristic equation det A minus A identity matrix is equal to 0 to find their eigenvalues, including the one whose eigenvalues are not real numbers. So to do this question, we need to use the equation det A minus lambda I. So instead of A, I use lambda is equal to 0. This equation is the characteristic equation of a matrix A. The solutions to a characteristic equation, or the characteristic equation, are the eigenvalues of A. So if we use this formula for tau1, we will get det, or the determinant of tau1 minus lambda identity matrix is equal to 0. If I now write in the matrix, we get 1 over root 2, 0, 0, minus 1 over root 2, minus lambda 0, 0, lambda is equal to 0. Hopefully we know that the identity matrix is 1, 0, 0, 1, and all I've done is just multiplied by lambda. So now we need to find the determinant of the matrix 1 over root 2 minus lambda, 0, 0, minus 1 over root 2 minus lambda. To work out the determinant of any 2 by 2 matrix, so that of A, where A is a 2 by 2 matrix, we do AD minus BC, and where the first term is A, this is B, this is C, and this is D. So this times this minus this times this. If we do that, we get 1 over root 2 minus lambda multiplied by minus 1 over root 2 minus lambda is equal to 0. When we now expand the brackets, we get minus a half minus 1 over root 2 lambda plus 1 over root 2 lambda plus lambda squared is equal to 0. These two cancel out, so we're left with lambda squared is equal to a half. Therefore, lambda is equal to plus or minus 1 over root 2. So we'd write that over here. So the eigenvalues of tau1 would be 1 over root 2 minus 1 over root 2. If I now do the same thing with tau2 over here, so that of tau2 minus lambda identity matrix is equal to 0, we will get the determinant of minus lambda 1 over root 2, 1 over root 2 minus lambda is equal to 0. That is because tau2 is equal to 0, 1 over root 2, 1 over root 2, 0. So when we do minus this by lambda 0, 0, lambda, we get this matrix. To find out determinant, we do this times this, which will be lambda squared minus a half is equal to 0. So lambda squared is equal to a half. So lambda, once again, is equal to plus or minus 1 over root 2. Doing the same thing with tau3. So tau3 is equal to 0 minus 1 over root 2, 1 over root 2, 0. So now using the characteristic equation, we get det tau3 minus lambda I is equal to 0. We get the determinant of the matrix minus lambda minus 1 over root 2, 1 over root 2 minus lambda is equal to 0. Finding out the determinant of this, we get lambda squared plus a half is equal to 0. So then we get lambda squared minus a half. So lambda is equal to square root minus a half. So in the question, we are told that one of the eigenvalues are not real valued. They're talking about this one. That is because we can't do square root a negative number. So we turn to imaginary numbers. And an imaginary number is defined by, so I, being the imaginary number, is equal to square root minus 1. So this I can rewrite as square root minus 1 times by plus or minus square root a half. So then square root 1 is I, so we get I times 1 over root 2 plus or minus. So we get I over root 2 plus minus as the eigenvalues for tau 3. So if we write that down, these two are the same, and then here we have I over root 2 and then minus I over root 2. And that's A done. Moving on to part B. For two 2 by 2 matrices A and B, we define the commutator of A and B as equal to A multiplied by B minus B multiplied by A. So this is called the commutator of AB. Show that the commutator of any matrix with itself A comma A is 0, and that A comma the transpose of A is equal to 0 if and only if A is equal to the transpose of A. So if we begin with part I, show that the commutator of any matrix with itself, so for example, A comma A is equal to 0. The commutator of A comma A is going to be A multiplied by A minus A multiplied by A. And of course this is quite trivial. If we have the same thing subtracting each other, we're going to get 0. So there's that. The next part, we have A and then the transpose of A, and we need to work out the commutator. I'm going to let A equal A, B, C, D, and that means that the transpose of A is going to be A, C, B, D. So to work out the transpose of any matrix, we just interchange the rows and columns. So here, hopefully you can see that this row has now become this column. If we now write out the commutator, we have to do A multiplied by the transpose of A minus the transpose of A times by A. And A is the matrix A, B, C, D. The transpose is A, C, B, D. And we have minus A, C, B, D multiplied by A, B, C, D. When we multiply this out, we get A squared plus B squared, AC plus BD, AC plus DB, and then C squared plus D squared. So that is just the rows times by the columns. Doing the same thing for the other pair of matrices, we get A squared plus C squared, AB plus CD, AB plus CD again, and then B squared plus D squared. If we now subtract these two matrices, we get B squared minus C squared. If we now subtract these two matrices, we will get B squared minus C squared, AC plus BD minus AB plus CD, AC plus BD minus AB plus CD, and C squared minus B squared. And all of this, according to over here, should be equal to 0. So if I write that as a matrix, it would look like that. So that means B squared minus C squared is going to be equal to 0, and AC plus BD minus AB plus CD is going to be equal to 0. So if we solve this, we get B squared is equal to C squared. So B is equal to plus or minus C. And this we can write as a product of two brackets. So if we put A over here, A minus D multiplied by C minus B would give us this. If we just need to check that, AC minus AB minus CD plus BD, which is what we have above. When B is equal to C, we get A minus D brackets C minus C, which is just 0. So then we're left behind with A minus D, 0 is equal to 0. So we get 0 is equal to 0. So A and D can be anything. So we have the matrix AD, and then because B is equal to C, we can just write B over here and B over here. So here we have A is going to be equal to the transpose of A. because when we swap around the rows and columns, we get the exact same matrix. When B is equal to minus C, we have A minus D bracket C plus C is equal to 0. So A minus D brackets 2C is equal to 0. So in this scenario, C must be equal to 0, which is what we get over here, or A should be equal to D in order to make this equation equal to 0. Because C is equal to 0 is already considered when we had B is equal to C, it must be now that this is the other solution where A is equal to D. If I have A is equal to D, we have the matrix A, B, and then minus C. Here, A is not going to be equal to the transpose of A. That means it's not a symmetric matrix. So when the question says, show that A, the transpose of A is equal to 0 if and only if A is equal to the transpose of A, this is not true. To make this true, A, the transpose of A is equal to 0 if and only if A multiplied by the transpose of A is equal to the transpose of A multiplied by A. When this is the case, if we scroll back up, when these two things are equal, of course we will get 0. So this is the condition that we need for this to be true. This is a normal matrix. As a normal matrix is defined by A multiplied by the transpose of A is equal to A transpose multiplied by A. So we could rewrite this as A, the transpose of A is equal to 0 if and only if A is a normal matrix. So basically, this is the definition of a normal matrix. Hopefully that made sense. Find the numbers f, I, j, k as those for which tau I, tau j is equal to the sum from k is equal to 1 to 3 of f, I, j, k, tau k is true. Show that f, I, k is equal to 0 and that f, I, j, k is equal to minus f, j, I, k, and calculate the f, I, j, k. Okay, starting with part I, we need to prove that f, I, k is equal to 0. What this is saying is ti, ti, so the commutator of ti and ti is equal to the sum starting from k is equal to 1 to 3 f(i), tau k, where k is going to take values of 1, 2, and 3. From before, we know that the commutator of two identical matrices will be 0. That's what we proved over here in part bi. So we know that tau I, tau I, the commutator of tau I, tau I will be equal to 0. So we have 0 is equal to the sum, where k is equal to 1 and 3, f(i), tau k. If I now separate this out and write it individually, we get 0 is equal to f(i), 1, tau 1, plus f(i), 2, tau 2, plus f(i), 3, tau 3. Now, tau 1, tau 2, and tau 3 are the same as the matrices that we saw in the first part of this question over here. And these matrices times by some constant is going to get us 0. What that means is f(i), 1 has to be equal to 0, f(i), 2 has to be equal to 0, and f(i), 3 has to be equal to 0. Because that's the only possible way to get these matrices to add together and make 0. Therefore, Fiik is equal to 0. So we've shown part I. For the next part of this question, we need to show that Fijk is equal to the negative of Fjik. So hopefully you can see that they've swapped around I and j. So if we work out the commutator of Ti, Tj, that is going to be equal to Ti multiplied by tau j minus tau j multiplied by tau I. And we also need to work out the commutator of tau j comma tau I, which will be equal to tau j multiplied by tau I minus tau I multiplied by tau j. So obviously these two things are very, very similar. If I factorize out a negative sign from this second commutator, we are left behind with minus tau j tau I plus tau I tau j. And this is the same as what is above over here. Therefore, we can say that tau I, the commutator of tau I and tau j, will be equal to minus the commutator of tau j, comma tau I. Now we know this is going to be equal to Fii1 tau 1 plus Fi, that should be a j, Fij2 tau 2 plus Fij3 tau 3. So that is that. And that's equal to minus Fji1 tau 1 plus Fji2 tau 2 plus Fji3 tau 3. If I now expand the bracket and write this over here, we get Fij1 tau 1 plus Fij2 tau 2 plus Fij3 tau 3 is equal to negative Fji1 tau 1 minus Fji2 tau 2 plus Fji3 tau, so minus Fji3 tau 3. If we now compare coefficients, this is going to be equal to that, this is equal to that, and that is equal to that, because the taus are the same. Therefore, just by inspection, we can see that Fij1 is going to be equal to the negative of Fji1. Yeah. So if we now do this for all the coefficients of tau 2 and tau 3, we see that that's the case with all of them. So Fijk is equal to the minus of Fjik. So therefore shown. And that's part II. Hopefully that makes sense. And now we need to calculate the Fijk, so the values of, let's say, F1, 2, 3. To do that, so let's say we were going to calculate F1, 2, 3, we are going to need to use tau 1 and tau 2. So tau 1 and tau 2 will be tau 1 multiplied by tau 2 minus tau 2 multiplied by tau 1. So here we get 1 over root 2, 0, 0 minus 1 over root 2 multiplied by 0, 1 over root 2, 1 over root 2, 0 minus 0, 1 over root 2, 1 over root 2, 0, and then 1 over root 2, 0, 0, minus 1 over root 2. If we now multiply these matrices, we get 0, a half, minus a half, 0, subtracted by the matrix 0 minus a half, 0, which is going to be equal to 0, 1, minus 1, 0. Now, we know that this matrix, so 0, 1, minus 1, 0, is going to be equal to f1 to 1 tau 1 plus f1 to tau 2 plus f1 to 3 tau 3. If we now replace tau 1, tau 2, tau 3 with the matrices that were given, we get 0, 1, minus 1, 0 is equal to f1 to 1 brackets 1 over root 2, 0, 0 minus 1 over root 2 plus f1 to 2, 0, 1 over root 2, 1 over root 2, 0 plus f1 to 3, which will be 0 minus 1 over root 2, 1 over root 2, 0. So if we now look at the first element in each of these matrices, we have 0, 1 over root 2, 0, 0. So we have 1 over root 2 times some constant plus 0 is going to be equal to 0. That means we know that f1 to 1 is going to be equal to 0. This now leaves behind 1 is equal to 1 over root 2 f122 minus 1 over root 2 f123. So that's me equating the second element 1 over root 2 minus 1 over root 2. And we also have minus 1 is equal to 1 over root 2 f122 plus 1 over root 2 f123. If I now subtract these two equations, we get 2 is equal to, these two cancel out, minus root 2 f123. That means f123 is equal to minus root 2. Using this, we can say therefore f213 should be equal to root 2. And that's from our proof that we made earlier that fijk is equal to negative fjik. So that would be f123 and 213. To work out f132, we have to do tau 1, the commutator of tau 1, comma tau 3. So that would be tau 1 multiplied by tau 3 minus tau 3 multiplied by tau 1. So we get 1 over root 2 brackets 1, 0, 0 minus 1, 1 over root 2 brackets 0 minus 1, 1, 0 minus 1 over root 2, 0 minus 1, 1, 0, and then 1, 0, 0 minus 1, and that's also times by 1 over root 2. So 1 over root 2 times 1 over root 2 is a half, and now if we multiply the matrices, we get 0 minus 1 minus 1, 0. Doing the same with the other set, we get a half, brackets 0, 1, 1, 0. If we now subtract the two matrices, we will get a half, 0 minus 2 minus 2, 0, which would simplify to 0 minus 1 minus 1, 0 when we expand the scalar. Now means that 0 minus 1 minus 1, 0 is going to be equal to f131 tau 1 plus f132 tau 2 plus f133 tau 3. Filling out tau 1, tau 2, tau 3, we get f131 brackets 1 over root 2, 0, 0 minus 1 over root 2 plus f132 bracket 0, 1 over root 2, 1 over root 2, 0 plus f233, 0 minus 1 over root 2, 1 over root 2, 0. Now, again, by inspection, we can tell that f131 is going to be equal to 0, and because over here we have a negative and then a positive, we cannot multiply this matrix by a constant to get both of the elements now negative. So that means that F233 is also going to be 0. That means we now need to figure out what F132 is going to be. So we need a number that can multiply by 1 over root 2 to make minus 1. So that number would be minus root 2. So 132 is equal to minus root 2. So that's F132 done. To work out F321, we need to do the same thing. So commutator of T3, T2 this time, which will be a half, 0, 1, 1, 0, 0 minus 1, 1, 0, minus a half, 0 minus 1, 1, 0, 0, 1, 1, 0. The halves is just coming from me doing 1 over root 2 times 1 over root 2. So we get a half, 1, 0, 0, minus 1 when we multiply the matrices, minus a half, minus 1, 0, 0, 1. So we are left with a half, 2, 0, 0, minus 2, which is equal to 1, 0, 0, minus 1. This is going to be equal to F231 tau 1 plus F232 tau 2 and F233 tau 3. Once again, just by inspection, we can tell that F232 is going to be equal to 0 and F233 is going to be equal to 0, and that just leaves behind F231, which must be equal to root 2. And because that's equal to root 2, F321 has to be equal to minus root 2. My apologies, this was meant to be tau 2, tau 3. So our final answers would be F231 is equal to root 2, and therefore F321 is equal to minus root 2, and then F213 is equal to root 2, and F123 is equal to minus root 2, and F132 is equal to minus root 2, so F32312 is equal to root 2. Hopefully that makes sense. This you can do in your own time on Google. Moving on to question 10. Suppose that a firm wants to acquire a quantity of labour L and a quantity of capital K to use for a production process with production function is equal to 2K plus 3L plus KL over 3. If the firm demands quantities of capital and labour KL, the labour and capital markets demand a wage and returns WR is equal to K over 2, L over 3. Write down the profit as a function of K and L and comment on whether it does make sense that wages and returns increase when the firm demands more capital or labour. Okay, profit is worked out by doing revenue minus cost. To work out revenue, we do price times quantity. We have the quantity, that would be our production function. Price, we do not know, so we're going to assume the price is equal to 1. So that would give us the profit equaling the production function, 2k plus 3l plus KL over 3 minus our costs. Our costs would be labour times by how much we paid their labour, which would be their wages, plus the capital, plus interest repayments on capital, which we have as returns here. So now if we substitute in W and R, we get 2k plus 3l plus KL over 3 minus L times W is LK over 2 minus K times R is KL over 3. So this and this go, and we are left behind with the profit function being 2k plus 3l minus lk over 2. And as a comment on whether it does make sense that wages and returns increase when the firm demands more capital or labor, more demand for labor should drive up wages as there's only a fixed quantity of labor. So I'd write as labor is fixed in the short run. And this could also be said about capital. Find the first order conditions for profit optimization and find the solutions. So we first need to find the partial derivative of the profit function with respect to k. So that would be 2 minus L over 2. And if we differentiate the profit function partially with respect to L, we get 3 minus k over 2. So 3 minus k over 2. So that leaves us with 2 minus L over 2 is equal to 0, and then 3 minus k over 2 is equal to 0. So 2 is equal to L over 2, so labor is equal to 4, and then capital is 6. So we get 6 and 4. I do believe that there's been a mistake here, and that wages should be a function of labor, and return should be a function of capital. So I am going to redo this question, but this time I'll be substituting in this. So wage is a function of L over 3 and returns is a function of K over 2. So doing the same thing again, we have profit is equal to 2K plus 3L plus KL over 3 minus KR plus LW, so labor times wages and capital times returns. When we do this, we get minus K squared over 2 minus L squared over 3. Finding the first order conditions now, we have the partial derivative of the profit function with respect to K, which gives us 2 plus L over 3 minus K, and the partial derivative with respect to L would be 3 plus K over 3 minus 2L over 3. If we now solve these, we have L over 3 minus K is equal to minus 2, minus 2L over 3 plus K over 3 is equal to minus 3. When we solve these two equations simultaneously, we get L is equal to 33 over 5 and K is equal to 21 over 5. Cool, so that's part A and part B done. Part C, determine the Hessian, calculate the eigenvalues of the Hessian in the local optima and classify them. In order to do this, we will have to find the second derivatives. So if I quickly jot down the first derivatives, we had 2 minus L over 2, and we had 3 minus K over 2. This gives us, for our second derivatives, when we differentiate the partial derivative with respect to K again, we get 0. When we differentiate the partial derivative of L again with respect to L, we get 0. When we differentiate the partial derivative of K with respect to L, we get minus a half, and that's the same when we differentiate with respect to K. We get minus a half. So our Hessian would be 0, minus a half, and 0. To work out the eigenvalues, we will have to use the characteristic equation that we saw before. So that's that h this time minus lambda I is equal to 0. So that minus pi minus a half minus pi is equal to 0. So we get pi squared minus 1 over 4 is equal to 0. Pi squared is equal to 1 over 4. So lambda is equal to plus or minus a half. So the eigenvalues would be a half and then minus a half. And as we see with the eigenvalues, 1 is positive and 1 is negative. It means that we have a saddle point. If we now do the same thing with our other first order conditions, we get, so we had 2 plus L over 3 minus K, and we also had 3 plus K over 3 minus 2L over 3. If we find the second derivatives, we get minus 1, and over here we get minus 2 over 3. Over here we get a third, and that's going to be the same over here as well. So our Hessian would be minus 1, a third, and minus 2 over 3. If we now find the eigenvalues of this matrix using the characteristic equation, we will have minus 1 minus lambda, 1/3, minus 2 over 3 minus lambda is equal to 0. If we find a determinant, we will have minus 1 minus lambda multiplied by minus 2 over 3 minus lambda minus 1 over 9 is equal to 0. Expanding these brackets, we will get 2 over 3 plus lambda plus 2 over 3 lambda plus lambda squared minus 1 over 9 is equal to 0. When we solve this, the two values of lambda that we get is minus 0.46 and minus 1.21. As both eigenvalues are negative, it means that the local optimum is a maximum. And that is the end of tutorial 3a. Hopefully that made sense.